Today we'll keep answering to Peter, and this time we'll speak on determinants. Answering to one of the previous questions about solving the systems of linear equations using Cramer's rule, we have unwittingly addressed the issue of defining the determinant. Back then, to define the determinant of the size 3 by 3, we used the method of triangles. A marvelous method, simple and easy to remember, but it does have a weak point though. It only works for matrices and determinants of the size 3 by 3. But what if we needed to calculate a determinant of the size 4 by 4 or larger? Practice shows that methods similar to the method of triangles in applications to determinants of the size 4 by 4 or bigger never simplify the calculations. They intricate them instead. So it is useful to know how to use a formula allowing to define a determinant of any size. And this is exactly what I am about to speak today. So this magnificent formula goes as follows. Sum of -1 taken to the power of I plus j times a ij times m ij. It only looks monstrous on the face of it, but if you look closer, you'll see that it's quite understandable. Let's clarify a couple of things first. First of all, the determinant can only be defined for the square matrix, meaning that the number of rows of the matrix must always match the number of the columns of this matrix. It is impossible to define a determinant for the non-square matrix, being of the size, say, 2 by 3 or 6 by 4 or whatsoever. Now, let's say we have a 3 by 3 determinant. In my case right here, circles are entries of a determinant or of a matrix. Each of the entries of this determinant may be given a number consisting of two indices. First of them goes for the number of row in which the element stands, and the second goes for the number of the column. Let's take this element, for example. This element lies in the second row and in the third column. Therefore, it may be given a number of 2, 3. Let's say A, 2, 3. Let's now mark all the rest of the entries. A, 1, 1, because this element lies in the first row and the first column. And then A, 1, 2, and then A, 1, 3, and then A, 2, 1, and then A, 2, 2, A, 2, 3, A, 3, 1, A, 3, 2, and A, 3, 3. Now back to our formula. Let's now figure out what stands for what in it. First, there is Aij. As we've just discussed, Aij is an element of a matrix or a determinant lying in the ith row and in the jth column. In our case right here, I and j can be set to the value of 1, 2, or 3, because our determinant is of the size 3 by 3. Then there is -1 taken to the power of I plus j. Considering the same element, a, 2, 3, we would come to the following expression. -1 taken to the power of 2 plus 3, because I equals to 2, and j equals to 3, which yields to -1 taken to the fifth, which is -1. Actually, this part of the formula can only be of the value of 1 or -1, because -1, I'm sorry, I'll write it once again, -1 taken to the even power always yields to 1, and -1 taken to the odd power always yields to -1. So this part of the formula only influences the sign in front of the expression. And now there is this mysterious Mij. Mij is the way in which mathematicians mark the minors of the matrix. Now, the minor is a determinant defined by removing the ith row and the jth column from the initial matrix. Let's see. If we wanted to define the minor for the element number A23, minor M23, we would cross out the second row of this matrix, or of this determinant, and then the third column of this determinant. And then the numbers left would form our new determinant. So our minor M23 would go like follows. A11, A12, A31, A32. Now we've defined all the components of the formula. Now let's try and learn how to use it. First of all, the rule says that we have to pick a row or a column by which the determinant will be defined. And then this means that if we picked a row or a column, we would set to a constant one of these two indices, I or j. And then the other one, the other index that hasn't been set to a constant, would change, and therefore it will form the summand for the formula. Let's try and write down the sum for the real determinant. First of all, we should pick a row or a column. By the way, you might ask, which row or which column should we pick? Strictly speaking, it doesn't matter which line would it be, but it's always better to pick the one containing the least possible numerics, like zeros, ones, twos, or so. So in our particular case right here, I would suggest to pick the row number 2 because it contains 0, 1, and 2. This means that the further calculations will be easier, will be more simple. So we're picking the second row. This means that we're setting I to a value of 2. Now let us write down the formula for this particular case. Delta equals to the sum of j changing from 1 to 3, because our determinant right here is of the size 3 by 3. And then minus 1 taken to the power of I plus j, but we have just set I to a value of 2, so we can write down 2 plus j at once. And then multiplied by a ij, then again we have set I for a value of 2, and then m to j. Now let us write this expression in detail, substituting j into the formula. This way we will obtain 3 summands, and each of the summands will contain a minor, which is a determinant for our particular case being of the size 2 by 2. Let's see how it goes. Minus 1 taken to the power of 2 plus 1 times a to 1 times m to 1 plus the second summand, minus 1 taken to the power of 2 plus 2 times a to 2 times m to 2, and then the third, minus 1 to the power of 2 plus 3 times a to 3 times m2, 3. As you can see, we've substituted j into the formula step by step, so we obtained first the first summand, and then the second, and then the third. Now let us substitute the numbers we already have into the formula. So minus 1 to the third power yields to minus 1, as we've discussed right here, times a to 1, which is 0, times the minor m to 1. Then minus 1 taken to the fourth power yields to 1. So we can simply write down plus a to 2, which is 2, times m to 2. And then minus 1 to the fifth is minus 1, times a to 3, which is 1, and then minor to 3. Now, as you can see, the first summand contains 0. This means that the whole summand equals to 0, and that we won't have to calculate the minor of the number to 1, which gives us less calculations already. But we do have to calculate m to 2 and m to 3. Right, let's rewrite this again. Minus m to 3.